All right. So as for, and by the way, this is probably going to be our last full lesson of the year, So exciting news there. We will have, I think, starting like the next 2 days, just like really brief mini lessons, just really quick mini lessons. Number one, this is on page 18, everybody. What wave types have the A highest energy and B lowest energy? Number two, what colors have the A highest energy and B lowest energy? And number three, blank nebula form at the start of the star life cycle, while blank nebula form at the end of a star's life. Okay. So number one, just so you guys know, the highest energy wave and the lowest, highest is going to be gamma rays. Lowest is going to be radio waves. Again, frequency perfectly correlates with energy. So the more frequent a wave is, the more energy it will pack. Kind of like gamma rays, right? Makes me think of like Superman with his gamma ray vision or light or laser beam vision. Also, the same reason why gamma rays can contribute to cancer, because they can deform cells, whereas radio waves are harmless for the most part. They're harmless and they're low in energy. We can listen to music from radio. Okay, and number two, the colors instead for the energy, highest energy color and the lowest energy color. We're talking about the rainbow spectrum here. You've got the violet being the strongest energy color of violet. Again, think of Roy G. Biv, right? Which, given that scenario, means that red is the weakest color energy, right? So red is the weakest energy. Violet has the strongest energy. Violet has the strongest energy. And then let's go ahead. And number three, guys, I didn't talk to you in much detail, so I'm gonna give it to you right off the bat here as well. Stellar nebulas start at the beginning of a star's life cycle, whereas the planetary nebulas are going to be at the end of the star's life cycle, right? So I'll keep that up for a moment. You can take a picture of it if you'd like. So when a star is forming and the star dust ignites from the nebula, that's the stellar, right? But then when it dies and it sheds its outer layers for the smaller stars, that's when you get a planetary nebula, planetary. Okay, moving on, and you can see that here, right? We can see, again, a stellar nebula is at the beginning, which is, again, much more organized and much more organized and well put together than this planetary nebula that happens when a star is dying, right? Okay, moving on to table of contents, 18 through 19 are going to be star classification. Give you guys a moment for that, star classification. All right, and let's go ahead and feel free to take pictures. If you have any issues with my pacing, anybody, let me know. Okay, let me go and update attendance. I think someone else joined us just a minute ago. Just Daniela. One moment, everybody. Okay, let me go ahead and go to our first question of the day. All right, what type of star is our sun? You need to answer in the chat for participation. Is it A, a dwarf star, B, a main sequence star, C, a massive star, or D, a neutron star? Again, what type of star is our sun? What type of star is our sun? Make sure you answer in the chat for the participation credit. Give you guys about 30 seconds, 30 seconds. Thank you, Sanaya. Thank you, Lakia. Got about 15 seconds, everybody, 15 seconds. Thank you, Damiona. All right, 8, 9, my bad, 6, 5, 4, 5 seconds, 5 seconds, everybody. A, B, C, or D? 4, 3, 2, 1. Again, Sanaya, Diego, Damiona, thank you for your answers, and Lakia. But I will say the right answer, and nobody got it, was going to be B, main sequence star, main sequence. Again, our sun is in a tiny dwarf star, right? But it's not a massive star. It's kind of in the middle. It's kind of in between. It's a medium. We call that a main sequence star. Call that a main sequence star. Okay? All right. Let's continue then to our topic of the day and what you guys are going to do then, and I'm going to, I'll kind of, well, we can just write it the way it says it, right? You guys are going to go to page 19 for this, page 19. Okay. And we're going to title page 19, we'll title it this. One second, everybody. Okay, you're going to title page 19 star classification. So ignore the 90, ignore the 20 there. And we're going to title this star classification, star classification. Okay, again, page 20, star classification, star classification. Okay, so these are different ways that we identify stars, and there are going to be 4 ways that we go over today. Again, star classification. Feel free to pause the video as you like. And I just forgot, I actually want to show a video with some questions on it. So what's that going to be here? All right, so here's our question. Oh, wait, no. Wrong slide there. Our question includes on page 18. Oh, not that one. Here we go. What will happen when the sun dies, and how many years will this take? Again, what will happen when the sun dies? So yes, the stars have a lifespan. They don't stay around forever. So for our star, the sun, what will happen to it when it passes away? And how many years will this process take? Okay. All right. So let's check this out. Again, feel free to take pictures as we go along. I'll leave it up for 10 more seconds in case you needed a picture. All right. Let's go and take a look at it. One moment. Okay. 3, 2, 1, 3, 2, 1. Let's check it out.
Like all stars in the universe, the sun is not immortal. The sun was born 4.57 billion years ago. It survives by burning 600 million tons of hydrogen atoms into helium atoms in its core every second. However, there is only a finite amount of hydrogen in the core of the sun. For the next 4 billion years, the sun will continue to fuse hydrogen to make helium. As more helium builds up, the core will shrink. As a result, nuclear fusion reactions accelerate. Faster fusion means more energy output. In 3.5 billion years, the sun will shine 40% brighter than today. At this point, Earth's oceans will boil, and the ice caps will permanently melt. All the moisture in the atmosphere will be lost. Life will not likely survive, and Earth will become brutally hot and dry, like Venus. After that, the situation gets worse. 5.4 billion years from now, the sun will exhaust all hydrogen in its core. The core will heat up and get extremely dense, but the sun's outer layer will expand a lot. It could expand big enough to swallow Mercury, Venus, and maybe even Earth. Even if it doesn't grow as far as the Earth, high temperatures will completely burn our planet. Once the sun has emptied its fuel reserves, it will become unstable, and as a result, it will begin to pulse. Each pulse will remove more of the sun's mass until all that's left is a cool, dense core. This core is called a white dwarf. The sun will spend the rest of its days as a white dwarf, slowly cooling and dimming as time passes. By this point, Earth will be completely inhospitable.
All right, so a number of stages will occur when our sun begins to die. Why? Because it's going to run out of the helium it needs to stay strong. But for our answer, here's what I want you to have, okay? We're just going to say this. It's going to become a red giant. It's going to expand as soon as it starts producing iron. Again, it needs helium, but it runs out. And eventually, you can kind of see it down here, right? It expands into a red giant. what's going to happen is that core is going to kind of collapse within itself, and all the outer layers of the red giant are going to be shed or dissipate, right? But the core will be left over, and it'll last for a long time. We call that core a white dwarf. We call that a white dwarf. So it'll be a red giant, and then later down the road, it'll be a white dwarf. And this process is roughly going to take 4.5 billion more years. So Earth has a long time to be around. Again, Earth, it could be consumed by the sun eventually, or easily it's just going to get too hot in this planet. So we're going to have to find a way to move to Mars, probably, which is further from the sun, live underground, or move to another another solar system with an Earth as well. Okay. Questions on that? We're all good? Okay. So let's go back to page 19. Page 19. We had the categories I wanted to go over, which were, as you can see here, star classification. And this is page 19, star classification. All right. So for this, we're going to include this about star mass. All right. So for star mass, and again, we would have research activities, but because we're online, I'm just going to kind of get right to the point here. All right. So we're just going to include what's in yellow here, all this stuff. Okay. And it says star mass. So all this other stuff, just ignore that. Okay. So what does star mass do? It determines the life cycle of a star. It determines the life cycle and the luminosity. So how large a star is determines how bright it is. The larger the star, the brighter it is. But if the star is smaller, it's going to live longer because it's using up less of its fuel, less of its helium, you could say, right? Okay. So that is star mass, Let's next take a look at star temperature. This is, again, all this is on page 19. All this is on page 19. Star temperature is determined by star color. Okay. That's how we indicate how hot the star can be. Now, if it's very hot, the hottest color can be is blue. The coldest color it can be is red. Okay, so color does a lot to tell us how hot stars actually are. Okay, remember our star is going to be a yellow star. We call this a yellow G2 main sequence star. We don't need to know the letters and what color they are, but just know again that the sun, our star, is a yellow G2 main sequence star. Okay. All right. Before we get into our last two terms, we got two terms called apparent and absolute magnitude. Those have to do with how we view stars differently depending on their perspective from space. These are important topics, these next two. Again, all this is on page 19. All of this is on page 19. Let's check out our last video of the day. What is apparent and absolute magnitude?
Another lens that astronomers use in magnitude is the concept of apparent magnitude versus absolute magnitude. Apparent magnitude is probably what you're most familiar with, and that's the brightness of a star as it appears to us. But with absolute magnitude, it's a little bit different. Astronomers will look at the brightness of an object if it were at a particular distance. So apparent magnitude, as you're looking at this picture, is the brightness as it appears to us, the observer. So, for example, this is the Pleiades star cluster. That has a relatively lower magnitude, which means it's brighter. And we're going to explore this scale in a little bit, so stick with me. But absolute magnitude is when scientists will measure the brightness of a celestial object if it was at a particular distance from Earth, that distance being 10 parsecs. So if we're here on Earth and a star was placed at 10 parsecs away, 32.6 light years, how bright would it be? So we can have two different values for magnitude based upon the lens at which you're looking at. So let's get an example of this. So this star right here, this is Aldebaran in the constellation of Taurus. It has an apparent magnitude of 0.87, so very close to 1, which tells us it's a bright object, but its absolute magnitude is negative 0.63. So this seems confusing because it's like, oh, does that mean it's brighter or dimmer? So I do want to go ahead and explore the difference between the negative, which are usually brighter numbers, and then the positive. The bigger the number, the dimmer it is. But I wanted to just
Okay.
go over this.
So we don't need to know all those details of those numbers, but I do want to know the difference between these two. So let's break these down, okay? So apparent versus absolute magnitude. Apparent magnitude, again, like I said, guys, this is all on page 19. Apparent magnitude is the brightness of the star compared to the view of it from Earth, right? So we're looking at how bright it is from the Earth. Whereas absolute magnitude is how bright it is from 10 parsecs away in deep space. Again, parsec is a unit of measurement for space. We'll learn about those other ones like astronomical unit and light years another day, but just know parsec is one of those, okay? And if you want to get an idea as to how what parsec is, a parsec is about 19 trillion miles. I think it's the farthest unit we can measure in astronomy. So pretty amazing stuff, Okay, that concludes that. Let's see, apparent and absolute magnitude. I think we've just about covered everything, everybody. That is it for our last full lesson of the year. We'll just keep things simple for today. We'll have one question per day. So we'll keep things simple. Let me go ahead and take attendance again. All right, and then we'll call it a day.